Welcome to the video lecture on cross-sectional areas and volumes. Now remember from a previous video lecture that we can use the disk method to find the volume of a solid with a circular cross-section. We can also use washers to find the volumes of a solid that has a hole in the middle as well. Now recall that the circular cross-section has an area of pi r squared. And we can find the volume of the region by summing up the areas of all these circular cross-sections using integration. This method can be generalized to find the volume of solids of any shape as long as we can find a formula for the area of the arbitrary cross-section. So what's going to be a little bit different in this video lecture is that our cross-sections are no longer necessarily going to be circles. Instead, they might be squares or triangles or rectangles. So instead of using a pi r squared inside of our integral, we're going to be using an area function inside of our integral, and that area function will vary depending on what shape it is that we're given. So if the cross sections of the area are taken perpendicular to the x-axis, then we're going to be using a dx integral, and we're going to integrate the area function for whatever the shape happens to be with respect to x, and these bounds a and b should be bounds for x's as well. If the cross sections are taken perpendicular to the y-axis, then the volume is going to be given by a dy integral, and we're going to integrate an area function in terms of y using y bounds. So for example, suppose that we have this shape here, this three-dimensional shape. You can visualize these cross sections here. I'm taking the cross section perpendicular to this x-axis. So it's crossing that x-axis, and the thickness of this little cross section is what I'm going to call delta x. Now this particular cross section has the shape of a square, and a lot of the problems that we're going to do today will be squares as well. So we'll need to find out what the area of this square happens to be. And whatever that area formula turns out to be is going to be called our area function. And that's going to be what we use for our a of x. Now because this is hitting that x-axis for our thickness, this means we're going to be using eventually here a dx integral. And the idea for these volumes is that what you're doing is you're approximating the volume by summing up all of these little cross-sectional shapes. And there's a whole bunch of them, right? You've got one here, and so forth. So if you visualize all these little cross-sections, they each have a certain area times a thickness, and area times thickness is volume. So if I sum up all of these little cross-sectional volumes, as I let that thickness delta x go to 0, then this volume v turns into a definite integral of that area function a of x dx, and this now becomes the exact volume. It's no longer an approximation. If we had our cross sections perpendicular to the y-axis instead of to the x-axis, this might be a dy integral. So it could be either a of x dx or a of y dy, depending on the orientation of the cross section. So our formula for this whole video lecture is that your volumes using cross sections will be the integral of your area function with respect to x, or your area function with respect to y dy, depending on whether you are perpendicular to the x or the y-axis. In the case of disks, when that cross section is always a circle, then this area function would be that pi r squared. So the disk method and the washer method are basically just specific types of these kinds of problems where the area function just so happens to be a circle. But we're going to be doing lots of problems today where that cross section might not be a circle. It might be a square or a triangle or a rectangle. So we'll have to use a little bit of geometry to help us figure out how to get its area. So let's take a look at some examples. Find the volume of the solid whose base is bounded by the circle x squared plus y squared equals to 4, with the indicated cross sections taken perpendicular to the x-axis. And in this first example, we want our cross section to be in the shape of a square. So the key to these is first drawing out what your base is going to be bounded by. And in this case, we're bounded by the circle x squared plus y squared equals to 4. So that's just a circle centered at the origin with a radius of 2. Okay, so there's my base. And now it's really difficult for me to draw this because it's a three-dimensional thing. So you're going to have to use your imagination here. But we want to take a cross-section perpendicular to the x-axis. So the x-axis is horizontal. So I need my cross-section to be vertical, perpendicular to that. So you want to draw a little slice, just like this. Now, imagine that coming out into 3D, coming out towards you, away from your computer screen, is a square that's popping out, where this slice that I've drawn here is the bottom of that square. So I'm going to take that square and I'm going to flop it over on its side, and this is what that square would look like. This side right here is this side. And then these would be coming out into space towards you, and then we would connect those across the top. So that's what this is looking like. And if you drew a cross section over here, then you can see that that square would be a little smaller. If I drew my cross section over here, then that square would be a little bit bigger. So you're going to get a whole bunch of these squares that progress in size, going up, 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 and then get smaller, smaller, smaller. Okay? So it's really hard to visualize that, but that's essentially what's going on. So because we have a square, the first thing we want to think about here is what kind of an integral do we want? Because we are going perpendicular to the x-axis, we're crossing or intersecting that x-axis, so our thickness is along the x. So that means this is going to be a dx integral, and the formula that we want to use is the integral of the area function a of x dx. So everything that we come up with here needs to be using x variables, and that includes the bounds as well. Okay, so now that we know the orientation and we know that we're using x's, next thing we want to focus on is our area function. Since this is a square, we need to know from geometry what the area of a square is. And since it's a square, all sides are equal. So I'm going to call each of these sides s initially. And the area of a square is just length times width, which in this case would be side times side, or side squared. So the area of a square is side squared. Now obviously that's not in terms of x, so we need to figure out what this side length is going to be, and it's going to be very similar to how we figured out radii when we were doing our disks method using volumes in a previous lecture. So what I'm going to do to find out how long this is, how long this side is, I'm going to find out this coordinate and this coordinate, and I'm going to find the difference in their two y values to find out what this height is, and that will be my s. And I want to do that in terms of x's. So if you look at these 2 points on the top and the bottom of the circle, they both share the same x coordinate. So they're both going to be x comma something. The y is going to be whatever this point is on the circle, and the y down here is also on the circle. So that's kind of misleading. How could that be? So what we need to do is focus in on our circle here a little bit and see what this is going to tell us. The y value would be whatever this circle is solved for y in terms of x, because I want to have x's in my answer. So let's solve this for y. So I'm going to subtract the x squared over, and to undo the square we take a square root, and when you take a square root you need a plus or a minus case. Now this is important because when we look at our circle here, when you graph this on your calculator, you can't graph a circle in this form. You have to solve it for y. And when you graph the plus case only, that's the top half of the circle. So the plus square root is going to be this y coordinate up here. When you graph the minus square root, that's the bottom half of the circle. So that's going to be this y coordinate down here. So that's how we get 2 different y's, but from the same equation. One's the plus case, one's the minus case. So now that we know these 2 y's, this side length s is this vertical distance, which is this y value on top minus this y value on the bottom. And remember, you always do top minus bottom. Be careful with your signs here. The top is going to be 4 minus x squared under that square root, minus the bottom, which is a negative square root. So a minus minus actually becomes a plus. They don't cancel out. And you get 2 of them. So you get 2 square root of 4 minus x squared. So this side length right here is 2 square root of 4 minus x squared, which means this area function is going to be 2 square root of 4 minus x squared squared, the side squared. And if you reduce that, 2 squared is 4, and the square and the square root cancel. So this becomes 4 times 4 minus x squared, or 16 minus 4x squared. So that is our area function that we're going to plug into my integral. So all of this goes right here. So here's my volume integral. 16 minus 4x squared dx. And my bounds are for x's. So what x's do I use? And we're using the whole circle. So the circle goes from -2 all the way up to +2. So my bounds should be -2 to 2. Okay, notice there's no pi at all because we're not doing circles. I mean, we had a circle for our base, but our cross section was not a circle. Our cross section was a square, and it's the square formula that's determining what we integrate. And we weren't integrating circles, we were integrating squares. Okay, so this is how it would be set up to actually get that answer. You could integrate. The integral of 16 is 16x. The integral of 4x squared is 4x cubed over 3. And then you would plug in -2 and 2 and subtract. So this would give you 32 minus 4 times 8 is 32 thirds. And then -32 minus a -32 over 3. And when you combine all that together, I'll let you do the arithmetic there, you get 128 over 3. Okay? All right, now the good news is most of the work that we've already done can be reused for part B. The only thing that's going to change now is the shape of our cross section. So we're still using the same base that we had before, that same circle, and these 2 points here and here are staying the same. X comma the positive square root and x comma the negative square root. And since we're still going perpendicular to the x-axis, this is still going to be a dx integral. The only difference is when I take this shape here and that slice and I flop it down on its side, now that side, it's not going to look like a square anymore, it's going to look like a semicircle. So this slice right here is this length, and then you have to imagine a little semicircular shape coming out in the 3rd dimension out from your computer screen towards you. And when you flop that on its side, this is what it would look like. So now what is our area function going to be? Well, it's a circle, a semicircle. So what's the formula for the area of a semicircle? Well, the area of a full circle is pi r squared, so a semicircle would cut that in half. So my area function that I want to use is pi r squared over 2, but I need to know what r is, and it needs to be in terms of x's because this is a dx integral. So how do we find our radius? Well, the radius would be from this center point to the edge, and this center point has the same x value that these 2 points had, but the y value is 0. So the radius would be this top y value, square root of 4 minus x squared, minus this center y value, which is 0. So the radius is just square root of 4 minus x squared. So now that I know that, I'm going to write down my area function, which was supposed to be pi r squared over 2. So this becomes pi times square root of 4 minus x squared squared over 2. When you simplify that, The square and the square root cancel out, just giving you 4 minus x squared all over 2. So my volume integral is going to become all of this. So there's your pi over 2 times your radius squared dx, and my bounds again for x were -2 up to 2. So the difference between the last problem and this next problem is that the area function is different inside because we had a different shape. So you're just using a different geometric formula to figure it out. So then to integrate that, you can pull that pi over 2 out front if you like, and then the integral of 4 is 4x, the integral of x squared is x cubed over 3. And then we would plug into that -2 and 2. So you would have pi over 2. 4 times 2 is 8, and this would be 8/3. And then 4 times -2 is -8, and this will be minus a -8/3. And then I'll leave, again, the algebra to you. And when you simplify that, get your common denominators and reduce, this is 16 pi over 3. Okay? All right, same situation again. So same base as before, same circle. Same slices going vertically. So automatically that means my volume is going to be whatever the area function is, dx. So everything is still in terms of dx. The x is determined by the fact that we're going perpendicular to the x-axis. These 2 points are still x comma the positive square root and x comma the negative square root. That hasn't changed. But now what we have to imagine is that this slice is now coming out with a height of 2 out straight towards you from the computer screen to form a rectangle of height 2. So if I were to take this and flop it down on its side, this side right here would be this side right here. And then when I flop it down, it's coming out a distance of 2 out towards us. And then we connect those tops, and there's my rectangle of height 2. So what's the formula for the area of a rectangle? Well, normally it's length times width, right? So the length would be whatever this is. And in the first problem we did, we called that S. And we knew what that S was. It was just the top point minus the bottom point. And when you subtracted, the minuses canceled out and you got 2 square root of 4 minus x squared. So this distance right here is that same S that we had before, 2 square root of 4 minus x squared. The width is this distance, and they're telling me that that is coming out a distance of 2. So the width is always 2. So my area function here is 4 times square root of 4 minus x squared. So my volume integral becomes the integral of this area function. There's no pi's in it because we're not doing circles anymore. We're doing rectangles. And the bounds for x still remain -2 to 2. Now this one would be difficult for us to integrate because you've got this square root function acting as kind of like an outer function. The inner function would be this 4 minus x squared, and the derivative of that wants to be a -2x, which I don't have. I don't have an extra x lying around to be able to make this look like pattern recognition. So this is actually really difficult to integrate. So at this point, until we learn some new techniques for integration, which we won't get to until the next chapter, you would probably just integrate this using function integrate on your calculator. And remember how function integrate works. It's under the math button on your calculator. You have to type in with parentheses the integrand first, which all of this would be considered the integrand, that function right there, comma x, comma the lower bound, which would be our -2, comma the upper bound, which would be our +2. So let me show you what that looks like on the calculator. So if you pull up your calculator, you're going to go to math, and it's function integrate, and it's number 9. So you can just press 9, or you could arrow down. And then you would want to type in your integrand, which was that function 4 square root of 4 minus x squared. Close the parentheses for the square root. Then you hit comma. Then you have to type in just a plain old x. That tells the calculator what variable to integrate with respect to, comma, your lower bound, which was -2, comma, your upper bound, which was 2, and then you close the parentheses and you hit enter. And this is really just a numerical approximation. So as you can see, this one's thinking about it a little bit. It takes a while for it to actually do the computation sometimes. And we get about 25.13. And this again is not a nice decimal, so you probably wouldn't be able to turn this back into a fraction using the frac button, because it doesn't look like that this is going to be a rational number. So we can just approximate it as a decimal, about 25.13. Okay, so use that function integrate command to check your answers or to integrate ones that would be difficult to do by hand. So this is approximately 25.13. Okay, let's try another example. Find the volume of a solid whose base is the area bounded by the lines f of x equals 2 minus x, g of x equals x minus 2, and x equals 0, whose cross sections perpendicular to the x-axis are squares. So you know you're doing these kinds of problems when the cross sections are shapes other than circles. So here we're dealing with squares. So first thing you want to do is draw the region that represents your base. So what we have is our base region bounded by the lines 2 minus x, which would have a y-intercept of 2 and an x-intercept of 2, and x minus 2, which has a y-intercept of -2 and an x-intercept of +2, and x equals 0. I only drew my lines up till that y-axis because I knew I was going to be bounded by the line x equals 0. So the region bounded by all three of these is this triangular region. Okay? Now, it's important in which direction you're taking your cross-section, and they will tell you which way to do it in the problem. So this one is telling me to go perpendicular to the x-axis. So the x-axis is horizontal, so my slice needs to go vertical. So you're just going to draw a little slice vertically like that. This is one side of my square, and then again you want to imagine two sides coming out straight towards you from the computer screen and then being connected across the top. So if I were to flop this over, then this slice side is the bottom, and then we have this square coming out towards us in 3D. Since this is a square, all sides are equal, and the area of a square is side squared. Now, what direction was our cross section? Well, it was perpendicular to the x, so it's intersecting the x-axis. So that means our volume formula that we're going to use is going to be the integral of a of x dx. So in other words, since our area function is this side squared, it's going to be the integral of side squared dx. But we need to figure out what this s is in terms of x's. Okay, so let's figure that out. Now to do that, we're going to find our coordinates again. So we need this top point and this bottom point. They both line up, so they both share the same x. The top point lies on this top line, which was our f of x, and its y value is given by this formula. So y is 2 minus x. The bottom point is on the lower line, which was our g, and its y value was given by this formula. So its y is x minus 2. So this distance between these 2 points is what we're calling our s, and that's just going to be this top y value minus this bottom y value. So the top y value is 2 minus x minus the bottom y value. Use parentheses here because we want to subtract all of it. So when I distribute my negative across, this simplifies into 4 minus 2x. So my s is 4 minus 2x, so that's what I'm going to change this s to right here. It's going to become 4 minus 2x quantity squared dx. So there's my side squared. All I need now are my bounds, and I'm ready to go. My bounds, well, I start at 0 for x and I go up to 2. That's where they intersect at. So my bounds are 0 to 2. Now to integrate, we're going to just go ahead and FOIL this guy out. So we'll get 16 minus 4 times 2 is 8, and I'll get 2 of those. So 16x in the middle plus a 4x squared. So when I integrate, I get a 16x minus, this is going to be an x squared over 2 times 16, and 16 divided by 2 would be 8, plus 4x cubed over 3, and now I'm ready to plug in my 0 and my 2. Notice again, there's no pi showing up. 16 times 2 is 32, 2 squared is 4, 4 times 8 is 32, 2 cubed is 8, so this will be 32 thirds. And then when I plug in 0, these are all zeros. These two guys cancel, so this is 32 thirds for that volume. Okay? All right. Now what would change if the cross-section perpendicular to the x-axis was an equilateral triangle or a semicircle? So we're still going to be using that same base shape, just like this. We're still going to be taking our cross sections perpendicular to the x-axis. So since we're going perpendicular to the x-axis, the volume formula is still area function in terms of x dx for both of these. The only difference is the area function changes. The area of an equilateral triangle, if you were to kind of imagine this being flopped down, this would be one side of my triangle, and an equilateral triangle has all three sides being equal. So if I call this side S, this is S, and this is S. Now you can derive this, or you can just take my word for it, but there is a shortcut formula for an area of an equilateral triangle. It's just like the area of a square, side squared, but then you multiply it by √3/4. And that comes from the fact that in an equilateral triangle, each of these angles is 60 degrees. So if you drop a perpendicular down, you get some 30, 60, 90 right triangles, and you can get the height of that triangle based on that. So it's easily derived knowing a little bit of geometry. So what happens is this volume integral becomes side squared √3/4 dx. And the same s that I had up here still applies, because this whole distance here was what I was calling s, and that turned out to be 4 minus 2x. And that's exactly this distance here that I'm calling s. So the s is actually the same for both of these two problems. So this would be, I'm going to take that √3/4 and pull it out, and I'm going to take that 4 minus 2x and plug it in for this s and square it. And you know what? We know what this integral is, because that integral is this integral. And we know the answer to that is 32 thirds. So when I go from 0 to 2, this becomes 32 thirds times that √3/4. So this answer will be 8, because 4 goes into 32 8 times, √3/3. So that one is actually fairly easy to solve after you've done all the work from the previous example. So now what changes if instead of taking these cross sections and getting triangles or squares, what if I take this little slice, flop it on its side, and it forms a semicircle? Okay, so now what's our area formula? Area formula for a semicircle is pi r squared over 2. So my volume now needs to be the integral of pi r squared over 2 dx. So I need to know what my r is in terms of x. Well, r is just this distance going from the center up to the top. So if you remember our points here, both of these share the same x, the top point was on the top function 2 minus x. So its y value was 2 minus x. And this center point is on the x-axis, so its y value is 0. So that radius would be this top point minus the center point, which is just 2 minus x minus 0. So the radius is 2 minus x. So this integral becomes pi times 2 minus x squared over 2 dx from from 0 to 2. We're going from 0 to 2 for x's. To integrate that, you can pull the pi over 2 out front. And here you have a couple choices. It's certainly okay to FOIL this out and then integrate term by term. I'm going to use a little pattern recognition. If I think of this as my outer function f and this as my inner function g, the derivative of g wants to be a -1, which I don't have, but I can put it in so that I have the right g prime and counterbalance with a negative. And now I have the f, the g, and the g prime. So to integrate, I just integrate that outer function, and the integral of a square is a cube over 3. And then that minus pi over 2 stays out front, and I'm going to plug in 0 and 2. So if I plug in 2 minus 2 is 0, so this goes to 0. If I plug in 0, 2 minus 0 is 2, 2 cubed is 8, so this would be 8/3. So negative pi over 2 times a negative 8/3 becomes a positive 4 pi over 3. All right, let's try another example. Find the volume of the solid whose base is bounded by the graphs of y equals x plus 1 and y equals x squared minus 1 with the indicated cross sections taken perpendicular to the x-axis. So first thing you got to do is draw your base region, whatever the region is bounded by. So we're bounded by the graph of y equals x plus 1 and y equals x squared minus 1. So y equals x plus 1 is just a line with a y-intercept of 1 and a slope of 1. So it's going to look something like that. And then y equals x squared minus 1 is just a parabola that's shifted down 1 unit. So it's going to look something like that. So the intersection of the two regions would be this shape right here. Okay? Now the second thing that's important is drawing in your cross section. We want to be perpendicular to the x-axis. X-axis is horizontal, so we want to go vertical. So you want to draw a vertical slice just like this, and it doesn't matter where you draw it. What you want to notice though is no matter where I draw it, on top I'm bounded by the line, and on the bottom I'm bounded by the curve. That's important. You want to be consistent, otherwise it would require more than one integral. Now that cross section forms a square in this third dimension. So you've got this square shape projecting out towards you into space. So if I were to take this slice right here and plop it on its side, it's going to form a square shape. If I call this side length S, then these are all S's, and we know that the area of a square is side squared. So my volume integral, because these are perpendicular to the x-axis, crossing that x-axis, this is a dx integral. So the integral of that area function with respect to x. And my area function, since we're talking about squares, would be side squared. So we just need to figure out what s is in terms of x, and then we'll know what to integrate. So how do we find out s? We find our points. So I need this point, and I need this point. They both share the same x. The top point is the line, and this is what y is in terms of x. It's just x plus 1. The bottom point is the parabola, and y is equal to x squared minus 1, so that's the y coordinate of the bottom point. So s is going to be this top y value minus this bottom y value, and use parentheses because you want to subtract all of it. So we want to distribute the negative across, and that's going to give me 2 plus an x minus an x squared for my s. So over here in my integral, this becomes 2 plus x minus x squared squared. There's my side squared dx. And now I need to know my bounds. And the bounds aren't obvious, okay? The bounds are going to be wherever this intersects over here, up to wherever this intersects over here. We need to know those two x coordinates of those intersection points. You may certainly do that using the intersect command on your calculator, or you can just take these two curves and set them equal to each other. So if I do that, I'm going to get an x squared minus x minus 2, which factors an x and an x, a 2 and a 1, a minus and a plus. So this intersects at positive 2 over here and negative 1 over here. So those are going to be my bounds. Negative 1 up to 2. This one, not too hard to do, but a little bit tedious because of the trinomial that you would have to square out, so that gets a little bit messy. So this would be a good candidate for using function integrate on. So if we pull up the calculator, this is how it would be typed in: 2 plus x minus x squared squared for the integrand, comma x, comma negative 1, comma 2, and you get 8.1, which you could leave it just like that, or if you wanted to turn that into a fraction, use that frac button under math, and that's the same as 81/10. So either answer would be perfectly fine. Okay, so there is our solution. So this is 81/10 or 8.1. Okay, so now what we're going to do is take that same region again, but this time our cross sections taken perpendicular to the x-axis are going to be rectangles of height 1. So let's draw our region again. We have that line, and then we have that parabola, and this is at negative 1, and this is at 2, and we're still taking our cross sections perpendicular to the x-axis, which automatically means we're talking about a dx integral no matter what, always, okay? The only difference now is when I take this side right here, which I'll call S, and I think about it being projected in space, we're going to form a rectangle of height 1 coming out. So the 1 is the dimension that's coming out towards you. So this is going to have that side length S, and then a height of 1, and then your side length S over here. So there's my rectangle shape. And the area of that rectangle would be length times width, which would just be S times 1, which is just S. So this volume integral that I would want to integrate would just be S of dx. And what's S? Well, it's the same exact S that we got up here because it's the same ordered pairs. So nothing changes in terms of that S. We can use the same S that we had earlier, which was that 2 plus x minus x squared. And here all we have to do now is integrate that. We don't have to square it because it's not a square, it's a rectangle with a height of 1, and length times 1 is going to stay that length. Our bounds remain negative 1 to 2, and since we're not squaring this one, it's not so hard to integrate by hand anymore. This would just become 2x plus x squared over 2 minus x cubed over 3 from negative 1 to 2. When I plug in 2, I get a 4 plus 4 over 2 is 2 minus 8/3. When I plug in negative 1, I get a minus 2 plus a positive 1/2 minus a negative 1/3. And then I'll leave it up to you to do the arithmetic there to get your common denominators, but this is going to turn out to be 4.5. Okay? All right. That concludes our lecture on cross-sectional areas and volumes. Just remember that for all of these examples, your volume is always the integral of your area function, either with respect to x or with respect to y, depending on whether your cross-section is vertical or horizontal, and that area function will be determined by the shape of your cross-section. Most typically, you'll see squares, rectangles, triangles, or semicircles. So you would use the corresponding area formula that you would learn in geometry. Draw your pictures, find your side lengths, and go from there. Good luck!